Okay, this problem's kind of neat. It's talking about Kobe, or a basketball player, jumping up really high and talking about the amount of time that they hang in the air. This is really cool. I never realized this. But let me give you the sort of motivation for the problem in the first place. They're essentially saying that if this is a height versus time graph, the spirit of the problem is basically asking you to show that if this is y max, and this is sort of the halfway point, y max over 2, they're essentially asking you to show that the amount of the size of this interval where they're above the halfway height is actually really, really large compared to the time where they're under it. And I guess the spirit of this problem comes from just the fact that parabolas are kind of have some concavity to them, right? If this was a linear equation instead, like that, then you wouldn't notice this effect. But because it's a parabola, you sort of have this like bowing shape to it, this bowl shape to it, that makes this interval so much wider. I actually didn't know this. I guess I don't know enough about basketball to have ever really thought about the the physics of it. But yeah. So let's identify some key points here, right? So if this is T naught, the point at which they leave the ground, this is T1, the point at which they hit y max over 2, and this is T2, the point at which they reach the max. And because of symmetry, we don't really need to care about these points coming down, right? We can just, the hint tells us to basically compare this interval to this interval, if I'm not mistaken. Yeah. Just to make it the wording a little bit more consistent with the problem, let's let T0 be equal to 0 as well. So sort of stopping the starting your stop clock, starting your stopwatch at 0. Okay. So when I was approaching this problem, I just said to myself, okay, we know some, like y max is, we're not given the explicit value, but we're kind of like, it's almost as if the problem is treating it like a given, so to speak. And I don't really know how to explain that other than saying that, the problem is sort of treating y max over 2 as a special value and y max as a special value, even though they don't explicitly tell you what y max is. We have some hunch that solving for things in terms of y max should hopefully help us a little bit. I don't know, maybe at the end of the day it cancels out, which is what I suspect is going to end up happening. But basically, I'm going to pretend that it's a pseudo known value for now. And I'm going to say that Vf squared minus V naught squared, excuse me. It's like V2 squared minus V naught squared is equal to minus 2G times Y max. And V2, of course, as we've always done, when you're at the top, your velocity is just 0. So this essentially lets us relate V naught to Y max. Okay, well, let's do something similar for the halfway point. So V1 squared minus V naught squared is equal to minus 2G Y over 2. Minus 2G Y over 2. And V1 squared is equal to, excuse me, I think I made an actual maybe error in my calculations here. Yeah, something very silly. The other thing that we know is that as the hint actually tells us, we can relate V naught to GT, because that's essentially saying, the kinematic equation where we say that change in V is equal to acceleration times time. Well, if we do that for the entire interval where he starts at the bottom and ends up at the top, that's essentially saying V2 minus V naught, the initial velocity, is equal to minus G times T2 minus T1, or T0, and this is just 0. And V2 is also 0. So this is essentially saying V naught is equal to G times T2. Okay. So far, I think so far so good. And that basically lets us get an expression for, I think that lets us plug it in for over there. Yeah, I'm sort of having to wing it right now because I realize I actually dropped a thing in my calculations. But the other thing that they tell us to hint is to do this exact same equation. Delta V is equal to, so this is the change, whereas this one was for the entire duration of the upwards leap, this one is just going to be for until he gets to the halfway point. But that's just going to look like A times T1. So between 2 and 1, and this is between 2 and 0. So that's essentially saying V1 is equal to V naught minus G times T1. Yeah, very complicated. This is one of those things where I'm just writing down so many equations, and eventually we just got to figure out how to solve this stuff. We do have a relation between V naught and Y max, and a relationship between V naught and T2. So by transitivity, that lets us relate Y max and T2. Sorry, I realize that this explanation is probably the one I've fumbled the most so far, but I'm hoping that at the end of it, we'll get some level of clarity.
I feel like this is another question, another like problem. If you get this, you could get everything else. To be
Yeah,
honest,
like I know that on my notes, I made one error that I can correct for, and I know that I could get this problem. It's just a matter of it's just gonna look very physically unmotivated. It's just gonna look like a big page of equations that I just sort of mash together and get a solution out of. And I realize explaining that to a student probably isn't the nicest thing. So I'm trying to create some sort of narrative here, and that's not always very easy to do. But okay, so we know that this is a special equation. This is an important equation. This is important, and this is important. Um, and what else do we know? We also know that Y max is equal to V naught T. V naught T2, right? So again, T naught is 0, but this is basically saying the kinematic equation for traveling in height. By the time you get to the maximum height in T2, it's minus 1/2 G times T2 squared. Yeah, this is not the neatest. But at the end of the day, we want to find an expression for T2 minus T1 over T1, which sort of means that we want to solve for T1 and T2 to get some expressions in terms of the other constants in the problem. And we don't want to put anything in terms of V naught or V1 because we're not explicitly told what those are. But here's what I'm seeing right now. Remember before I said we could put V naught and Y max in terms of each other? And this lets us put T2 in terms of Y max. So this lets us put something like T2 is equal to, something something Y max. Okay, that's progress. That's really good so far. Now we want to say something about T1, right? If we can say something about T1, then we're probably done, to be honest with you. The only time I see T1 in these equations really is unfortunately over here. So T1 is related to V1 and V naught. Well, okay. Like before, we said that we knew how to put V naught in terms of Y max, so we can plug that in over there. But what is V1? Ah, yes, here's what V1 is. V1 we can put in terms of V naught squared, right, which can come down from above. And in terms of Y max. So we can put V1 squared also in terms of Y max and plug that in. So this lets us isolate T1 in terms of a bunch of Y max terms. And then once we have T2 and T1, we plug them into this equation, and we're done. How are you all feeling right now? I think that was probably the worst explanation I've given so far this night. But I want you to know that this problem is possible.
This seems like a Chegg problem.
This seems like a Czech problem.
A Chegg
A
problem.
Chegg problem? Well, fundamentally, everything I've written here, like every individual equation seems reasonable, right? Sometimes in physics, if you don't know exactly what to do, just writing down every single valid equation that you have in the situation, is sort of the default move after you've checked the more obvious options. But the point is, working backwards and sort of reverse engineering the motivation, we're trying to figure out expressions for T2 and T1. And those come from the V naught is equal to GT2 and V1 is equal to V naught minus GT1 equations. Right? So at this point, we're basically just trying to figure out ways to express V naught and V1 in terms of Y max. And that's what these two equations are for. Yeah.
Are these being recorded?
They are.
Okay.
Yeah. Hopefully that makes it takes a little bit of the pressure off. I don't think this equation ends up being super useful now that I'm thinking about it. Perhaps you can get away with just using these two and plugging them in over here and here. I'm sure there is a way to do it with this equation, but I guess that's not how I thought about it. Sorry, folks. Am I scaring you?
No, I'm just questioning how long this is going to take me.
Questioning how long this is going to
This-
take?
Yeah, this question when I just go back to the recording. Slowly.
Yeah. Okay. But like, do you see that there is a solution? Like, there is an outline of a solution on page here.
So it won't be a numeric answer, or will it? Or be like an equation at the end?
Yeah, that's a really good question. So they don't give us any explicit numbers, right? But I bet you what's going to happen at the end of this expression is going to be a bunch of stuff times Y max and a bunch of stuff times Y max for T2 as well. And my bet is that all the Y maxes are going to cancel out and end up with a genuine fraction. I bet you're just going to end up with a real fraction number between 0 and 1. And I think that'll be great. Yeah, I'm probably going to compute this myself because I think it's pretty neat, and I'm very curious what the final answer is. I never really thought about basketball this way. Yeah. Let's have you all, work through this problem over the week, and if it turns out to be, really difficult still, maybe I'll try to redo an explanation for it. Okay. Yeah, I might be able to find a simpler way to explain it or motivate it.